Thank you for the introduction, and good morning to everybody. What we will cover today is what transforms a geothermal project into a success. We will then go quickly through the various technologies that are available today. Then we'll go through several case studies, starting with Puna, and hopefully we'll have the time for the other two. And then we will summarize. Okay, just a brief introduction of ORMAT. ORMAT has celebrated its 50 years anniversary last year. We are mainly focused on the organic raining cycle, and we are in the geothermal business for more than 35 years. We have, in Iceland, we have some of our first, what we call OECs, ORMAT energy converters, installed in the Svartsengi. Part of them are water-cooled, the others are air-cooled. We already installed more than 2,000 megawatts all over the world in more than 150 plants. We also, as a company, we design, we fabricate, and we also own and operate our own power plants, mainly in the US and Kenya, with over 700 megawatts. We have more than 1,000 employees, and we have 600 revenues in the year of 2015. We are capable of offering a supply of equipment. We can offer an EPC, and we can offer also, besides the equipment or the power plant, we can also do all the balance of plant from the resource to the power plant and back to the reinjection. What transforms a geothermal project to a success? First of all, and probably the most important, is the properly developed resource. If we know in advance the resource, then we can match the best solution. The second one, of course, is the choice of the right technology. The operation maintenance, if it will be simple and cheap, it will help the profit of the power plant. Then, over the years, to properly maintain the resource, and a flexibility to change the equipment according to the changes in the resource. I will focus on the choice of the equipment. Okay, I'll just go quickly through the various technologies, because I'm sure that you are all of you are familiar with it. This is the marker. Okay. This is the traditional steam power plant. We take the steam out of the flash tank. The steam is going into the steam turbine, expand for electricity generation. Part of the steam is used for the ejectors, together with the vacuum pump, to draw the NCG out of the condenser. Probably this is the most complicated part of the equipment, besides the technology of making the turbine, mainly the materials appropriate for the characteristic of the steam. The brine can be either flashed to a second flash, and when the steam is going to in the middle of the expansion, or rather going into back to the injection well. The application it's mainly used in medium pressure steam. We are talking right now, most of the technology are for 8 to 8 bars inlet, mainly due to the wetness at the last stages. It can use either B-phase steam and brine, when brine flash to second flash, or a dry steam, and it's mainly used where NCG content is low. The benefits are, of course, the high efficiency of the steam turbine and the large capacity. We know that, I think in New Zealand, there are turbines of more than 200 megawatts. The drawbacks of the steam technology are the direct contact between the steam and the turbine blades. The high pressure of steam causes excessive wetness in the turbine last stages, What we are familiar today is that wetness should not be above 15% at the last stage. The energy and the power that are used to suck out the NCG from the full vacuum to the atmosphere, and the condensate, which is being used as a makeup for the cooling tower, is not reinjected to the back to the earth, and thus there is first of all, there is less resource that is going back into the ground, and it is more prone to scale because all the solids remain with the brine injection and can cause the injection well to be blocked. And of course, the last one is the visual impact and large structure of the cooling towers, the turbine building, and the plume. With the ORC solution, we have several solutions. We have the conventional binary, where only brine is used. Only brine is used. Over here, it preheat and evaporates the fluids, the organic fluids that go through the turbine to the condenser and back. The binary can also have a use of a two-phase, steam and brine. Steam generally feeds the vaporizer, and brine goes to the preheater. And then a combination of a steam turbine and then a bottoming ORC. The steam first enters the steam turbine, and the exhaust at above atmospheric pressure goes into the bottoming cycle. With the integrated geothermal combined cycle unit, we also use the brine for a brine ORC. The binary is used generally for brine-dominated or high and medium enthalpy resource where we have a B phase. It can generate the electricity, as I said, from both steam and brine. Today, as the lecture before, we can reach, the size of an ORC can reach up to 30 megawatts. I'm sure that in the next few years, it will approach 40 megawatts. Mostly air-cooled, thus 100% reinjection. The mixture of condensate and brine complements each other, so minimizing silica scaling and greater reservoir support. There is no contact between the steam and the binary fluid and the turbine blades. There is no need for energy to dispose the NCG, and throughout the years, due to changes in the resource, an ORC can easily be adapted to changing in resource characteristics. A GCCU, geothermal combined cycle unit, which first, as I said, enters the steam into a steam turbine. In that case, it can use a very high pressure for geothermal high pressure steam, 24 bars. It can also use or handle high NCG content. The benefits are that the high pressure, we can use the energy of the high pressure steam without having any excessive wetness at the last stages of the steam turbine. The NCG is released to the atmosphere at above atmospheric pressure, so there is no need to any energy to dispose the NCG. Since the bottoming unit can be air-cooled condensed, there is a 100% reinjection of the condensate or the steam condensate and the brine back to the earth. Okay. This is a Puna, which we'll talk later. With the integrated GCCU, we have the same benefit as before, but we also use the brine to have more power output through the brine ORC. This is a Bokai from New Zealand, and it uses high pressure steam at 19 bar It has a steam turbine, a bottoming ORCs, and a brine ORC. And what we can see here is, and this is one of the benefits is that, first of all, throughout the years, due to the 100% reinjection, the power plant, they saw that they have an increase in enthalpy, and at 7 years after the installation, they added another bottoming OEC, and 7 years later, they changed one of the brine OEC into a steam-fed OEC. And by that, of course, they increased the power output of the plant. A brief comparison, we'll just go through the main issues. CapEx, we believe that ORC is the lowest, while the STG plant will be the highest. Size, of course, the STG can be up between 15 and 200 megawatt, while ORC today, as I said, between 1 and 30 megawatt. Of course, as the lecture before me, it can be, of course, lower than 1 megawatt, but we believe that in geothermal, this is a minimum range. And in the IGCCUs, there is, of course, any combination between the steam turbine size and the ORC sizes. Availability, we believe that in a ORC cycle, because there is no connection between the resource and the turbine, the availability is much higher than in the case of direct use of the steam in the steam turbine. Steam purity is important in STG and, of course, in the GCCU cases, while there is no importance in the ORC because the steam is going through the tubes of the heat exchangers. Acid dosing, because we do not re-inject all the resource back to the earth. Acid dosing generally is mandatory in STG, which is not required in the other technology. Steam scrubber is mandatory for both technologies that use steam turbines. Vacuum system is required only here, and the size depends upon the NCG, the steam pressure for the ejectors, and the cooling water for the liquid vacuum pump. Only in the ORCs there is no direct contact between the steam and the turbine. We believe that ORC is a shorter time to commission, and in IGCCU probably it can be done in stages. Flexibility to changes in resource with the ORC and the IGCCU, it is higher than in the case of the STG. Okay, plume, there is no plume. In the case of ORCs, there is no plume because it's mostly air-cooled. Of course, it can be water-cooled, but generally ORC use the air cooling. And I think that one of the main issues is the reinjection. And we heard yesterday about depletion in pressure and resource here in Iceland. This is because for the STG, the steam that is condensed is used for the cooling tower as a makeup, and the reinjection is only 60% of the total resource that is going into the plant, while in the ORC, any technology, it is up to 100%. And here we have the impact of the partial injection with the STG versus the other technologies. Turbine damage is scale deposit. Also, it was discussed before. It's severe with the STG, of course, also with the case of GCCU, but there is no, this is not the case on the last stages, which are here at the pressure of above atmospheric, and here it's going into a very low atmospheric pressure. You can see here examples of open turbines. This is an organic turbine versus a steam turbine. And regarding the visibility and plume, in New Zealand, this is a Rotokawa. This is a Rotokawa 2, a steam turbine. Over here, behind the trees, this is the GCCU plant. You can see there is no plume signs. Okay, now we will go through the case studies. The first one is Puna. Puna was developed by ORMAT in 1992 and is still operating since then. The resource is steam and brine and 14 bars. The project requirements were 100% reinjection, zero emission. Since it was a major power producer of electricity in the island, it has to be capable of dispatch mode, and I think one of the gentlemen over there asked before about it, and this power plant is capable of dispatching the power and provide frequency and voltage control. The solution is selecting only air-cooled unit, which requires the binary. We implemented the 10 GCCU with a total of 30 megawatt. What we did is that we took the 19 bar steam, entered into a 4-stage steam turbine. The exhaust pressure is 2 bars. The wetness in the last stage was 8%. After the steam is flowing out of the steam turbine, it condenses in 10 bottoming cycles. The steam that is the NCG, with some the residual steam that still exists with the NCG, are collected to a common header. Then we have an air cooler to condense as much as possible of the steam. And then it is the NCG with a mixture of 60% H2S and 40% CO2 is compressed by a 2-stage compressor with intercooling, 75 horsepower, and it is being injected into the condensate return line, which makes the plant to be with zero emission. What helps us to do this injection of the NCG into the condensate is, of course, the low amount of NCG, only 0.2% of the steam, the very low return temperature of the condensate, about 60 degrees centigrade, and the high amount of the relative high amount of H2S in the condensate, which is 60% out of the NCG. Just to emphasize, all the original system, the generating unit equipment and the NCG equipment, still operating since 1992. Still, after 20 years of operation, there was some decline in enthalpy, but not in flow, mainly in enthalpy. And in order to boost again the power of the power plant, in 2012, an integrated 2-level unit of 8 megawatt, which utilized the brine only, was installed to increase the power to 38 megawatt. We have, due to the high silica in the brine, we have a pH modification system in front of the system, which enables us to delay the silica precipitation in the heat exchanger and in the reinjection lines. This is a general PFD. We have the GCCU. This is the system with the air. This is the NCG injection system, compression system. We have here the air coolers and the two-stage compressor, and into the condensate line. Another case is the Natamariki, a 100 megawatt power plant, utilized 4 OECs. The resource is again 14 bars. Reinjection is at 90 degrees centigrade with the silica scale index of 2. Customer request, because of prior experience, to have only to have 100% reinjection and minimizing O&M cost. This is the general overview of the power plant. What we can see here is that even though probably STG would provide 6 megawatt more than an ORC system, the client, he requested to use a binary system, which is air-cooled and makes full reinjection of the fluid. The 6 megawatt, if we would have done this power plant today, since the installation, we developed some issues that would boost the power output to 87 megawatt and probably decrease the difference to only 2 megawatt. Okay. I will just go shortly, another case is of high NCG. You can see here that due to the STG, due to the power required to take out the NCG is very high, while in the ORC or in the IGCCU is very small. So with the IGCCU can give 5 megawatt more than an STG. On the total megawatt hour of production, it is above 40,000 megawatt more power output. Just to summarize, when we are looking at a geothermal power plant, we have to look at the resource, of course, the efficiency or the power output, and to do the best matching between the technology and other factors like sustainability of the resource, system simplicity in order to have the operator to have a simple operation, simple maintenance, reservoir management, and of course, environmental consideration. We in ORMAT, we believe in injection of 100% of the resource to sustain the resource and keep it as constant as possible. And with the last item, no thermodynamic cycle provides a total solution for all enthalpy cases. The optimum cycle shall be selected according to specific site conditions and all other requirements of the power plants. Okay, thank you.